Hi there, and welcome to this lecture on population. Specifically, we are going to be looking today at population dynamics and carrying capacity, and this starts in your notebook on page 21. So part one of this lecture is going to be population dynamics, and to be dynamic means that a population is changeable in many ways. So the concept covered in 5.3 is what limits the growth of populations. No population can grow indefinitely because there's going to be limits to resources and because of competition. And that makes sense from what we see in nature. A forest cannot support an unlimited amount of deer because there's competition for the resources. Those who are weak and ill-suited will die off, and those who are the strongest or the best able to adapt will survive. There's also going to be this will relate to a feature that we'll call carrying capacity, and that'll be the last part of this part one lecture. Okay, so in what ways are populations dynamic? Well, the things that can change about a population are their distribution, their numbers, and that really means just simply the size, and the age structure of a population. And we will talk about these factors as well when we start talking about humans in chapter 6, which is our next unit. And especially in people, we can see this very clearly in the United States, that the age structure of our country has changed dramatically, where we used to be more predominantly in the labor force because of those baby boomers, and now we have an aging population, a geriatric population, and there are some worries that will come along with that in chapter 6. But the same thing can be said of animal communities. And so these things are dynamic parts of a population. So again, dynamic means it changes. And these changes can be because of four basic reasons: temperature, presence of disease organisms or harmful chemicals, resource availability, and the arrival or disappearance of a competing species. And all of these are things that we've talked about so far before. We talked about temperature back in the last unit, and of course with global climate change becoming a more accepted reality, we know that organisms are having to migrate, and so that will change their population. Also, you can just think about the presence of mosquitoes and when you would see them out versus not being active and being dormant. So temperature has a lot to do with a population and when it might be visible and when it might be reproducing and spreading its numbers. Presence of disease organisms or harmful chemicals. If you remember back in Walk in the Woods, talked about diseases that can come along and kill the hemlock forest, the chestnuts. It might be a bug, it might be a fungus, but we definitely see this in nature, and it can have a devastating impact. Think back to the Irish potato famine caused by a fungus. Harmful chemicals, I know in my class I showed you the atrazine effects on frogs, and we know that that's going to definitely have an effect. If you are a four-legged frog, you're not going to be a viable specimen, and you're not going to be able to pass on your genes. Resource availability. If resources become scarce, your population is going to suffer. And the arrival or disappearance of competing species. Again, think about that cane toad. That video is going to come up again and again. Those exotic and invasive species, also just a species that might come in as time progresses. It also might be a species we reintroduce, like the wolf, but those will all have an effect on a population. Okay, so how are populations distributed? This is one of our major factors that determines population characteristics. So how are they distributed? They can be clumped, and it means just what you think it means. They all live together in one specific area. They can be uniformly dispersed, or they can be randomly dispersed. And we're going to look at a couple examples of this. So clumping, and clumping would be, again, everybody is all together. Clumping is a great thing for especially a prey species to do because they are going to have security in numbers, and that's the that's the third thing on this list: protection from predators. And I think often about the elephants, which will circle up in a matriarchal, all the mothers will circle up around their young if there's a potential predator out, maybe a lion. It could take down a baby elephant, but it's not going to take down a big elephant. And so the mothers will all gather up, and that clumping and that matriarchal pack that they go in is really going to help protect their population. The first one, species tend to cluster where resources are available. Again, I like to think about Africa. I like to think about the movie The Lion King because that's a great one to show some of these things. Think about the wildebeest herd and think about the gazelles, the antelopes. Africa is a great place to see this in large scale. You have big, big clusters of organisms, and they migrate to find new grass, new pastures when what they've eaten up has gone away. Groups also have a better chance of finding clumped resources. If you are in a group, like let's say ants, they might send out a couple pioneer ants to see what's out. They'll scout it and they'll report back and they'll leave a chemical scent and everybody can follow them. So if you're in a group, you can have that added benefit of more eyes looking for those resources. If you're a predator, packs allow some to get prey where they might not before. And again, I think of lions, specifically lionesses, and they're going to hunt together. It's very unusual for large predators to do this, but these cats will do it. The females all get together to hunt, and then this also allows their young to get food. They get more food hunting this way than they would hunting separately. And you also have temporary groups that might only appear seasonally for mating and for caring for young. Think about happy feet and the penguins. The penguins in Antarctica do this. It's the only time when they gather together is when the males need to take care of the eggs and the females need to go out and find the fish resources. And that clumping together helps to increase their group temperature. It helps them to all take care to hatch and raise those young. But that's just a temporary group for the breeding season. Population size. Okay, so the second thing after how is a population grouped up, whether it's clumping, evenly distributed or randomly distributed, the next thing is going to be their numbers. Population size is governed by births, deaths, immigration with an I, and immigration with an E. The way that I always remember this is with an I means they are coming in, with an E means that they are exiting. And we will see this again with people. So I is in migration and E is exit migration. If you remember it that way, you won't have any problems. So we end up with an equation, and this is one of the equations that you will have to memorize. And the equation for population change is very simple. It's who's new minus who's gone. So the new people are going to be those that are born or those that move in, and you subtract from that those who have died or those who have exited your population. So it's a very simple equation. You simply have the new people minus those that are gone, and you just have to remember that to be new, you're born or you move in, and to be old, you die or you move out. Very easy equation. We have to regulate this, though, for the size of our population. So we use a rate. We don't typically use straight numbers. We use birth rates, death rates, and migration rates. And those rates are per 1,000. Okay, and then the last thing where we said a population could be dynamic in its age structure. We break up an age structure into three specific categories: pre-reproductive, reproductive, and post-reproductive. Your pre-reproductive age is actually, and this is global averages, it's not something that is set by culture, it's simply set by biology. So pre-reproductive is currently set at 0 to 14. Now we know that people are capable of reproducing earlier than that, but it's not considered medically sound. Most of those pregnancies are going to have complications. And so true reproductive age starts at 15. Again, pre-reproductive 0 to 14, reproductive age 15 to 44. Okay, so 44 is the end there of our reproductive years. Post-reproductive would then be 45 and up. And so we think about that in light of changing American population or world human population, and we know that people are starting to live longer. So we're spending more years in our post-reproductive age. Now again, that's just for people, those distributions. For animals, it's going to be completely different. Rabbits can start reproducing 6 months of age or younger. You have other animals, like let's say an alligator, that might be 7 years before they are reproductive. And so the age structure, though, is going to help determine who's reproducing and who's not. If you've got a very young or a very old population, you can't grow your numbers. You can't grow your numbers until everybody is reproductive. Okay, no population, though, can grow indefinitely. There's going to become a limit at some point. So we're going to look at J curves and S curves. A J curve is a curve of exponential growth where the population just keeps booming and booming. And this is what the human population has done lately. This happens when you have high biotic potential. Biotic potential is how many kids can you have? How many offspring are you even capable of carrying? Now, again, for humans, it's very, very low. Our biotic potential maxes out, again, usually at one. Some people will have twins or triplets naturally, but our biotic potential tends to be carrying one child. Think about other organisms. You have a lot of shark species that can only have 2 babies at a time. Some dog species will have maybe 8 for a very, very large dog species, or I'm sorry, dog breed. But that's the idea of biotic potential. A bacteria, extremely high biotic potential. Rats, roaches, rodents, all of those have very high biotic potential. And another way to say that is that they have a high intrinsic rate of increase. Without any limitations, if they have plenty of resources, they can reproduce very, very quickly. So we call that a high R. R, think of it as standing for reproduction. Roaches, rodents, rabbits. I always think of those R's and it makes great sense. That is a R selected species. We'll talk about that later on in the next lecture. These species reproduce early in life. They have short generation times, which means they can have lots and lots of babies. One litter of rabbits followed the next month by another litter of rabbits. They can reproduce many times in their life, and they have many offspring each time they reproduce. So lots and lots of population growth built in, which leads us to an exponential or J-shaped growth curve. The size of your population will eventually hit a limit, though, and the limit could be things like light and water, especially if you're a plant, space, nutrients. Again, these are very heavily plant related, but ecology should be based in plants. They're our producers. They give us our NPP, or net primary productivity. You could also have exposure to too many competitors, predators, infectious diseases. And so these things present a limit. They're going to be a pressure pushing down on the maximum capacity your population can have. This is termed environmental resistance. It pushes down on the capacity of your population to grow. It ends up giving us what we call big K, the carrying capacity. The carrying capacity for a population is the maximum number of individuals that can be supported by one area. Again, so if you don't have any limits, you just get to go with your biotic potential and you grow exponentially. But as soon as there's resistance, as soon as there's pressure from the top, you have to level out your population growth. And then it becomes a logistic or an S-shaped curve. Okay, so this leads us to the idea of carrying capacity. Again, I said it's a maximum number of individuals supported by an ecosystem indefinitely. This has to be sustainable to be a carrying capacity. So here's the graph, how everything looks. Now, if you follow my mouse here, in the beginning, you've got a J-shaped curve. You can see the exponential growth, and again, it's determined by your biotic potential. How fast can you reproduce? You can be J-shaped without being a rat, roach, or rabbit. You can be like this as the human population is, but eventually populations are pushed back by environmental resistance, limits placed on the amount of resources available, and this gives us this line that we call carrying capacity. If you ever have to identify it on a graph, look for that place where the population hovers. It goes up and down right around there. Too low, populations grow because biotic potential. Too high, they die back because of environmental resistance. And I'm going to stop there and continue with part 2.